Hi, it's Ryan. This is our second example using Kirchhoff's rules. This example has the circuit drawn with two power supplies. And in this example, we're going to determine the current through, the voltage across, and the power dissipated by each resistor in the circuit, which is shown below. We're also going to give a possible real-world application for this circuit. So when all is said and done, we're going to come up with something that this circuit may be actually used for. And so here's our circuit. We're given the voltages and the resistance values for everything, and we're asked to apply Kirchhoff's rules. And so we're going to have to start by applying those conventions and labeling our currents and loops arbitrarily. And so I'm just going to kind of stick to the same sort of way I've been labeling currents. I've always been labeling currents leaving the positive part of a power supply. We can call this maybe I1. And if we have I1 leaving V1, then we should have I1 returning to V1. It looks like I1 approaches and hits a junction. I'm going to do junction in blue for this one. Junction 1, and then obviously then there's junction 2. I1 is going into junction 1, and that means that I2 and I3 will leave junction 1. Oops, I'm sorry. I wanted to stick, so we're doing this at random. So I'm actually had originally said I'm going to draw my currents leaving the positive terminals. So I'm going to draw I2 leaving V2. And if I2 leaves V2, then I2 needs to return to V2 as well. And then we're just left with an I3 to go through R1. So I've, in a sense, arbitrarily chosen directions for my currents. I just stuck with current leaving the positive terminal like I kind of always have. And we'll let the Kirchhoff's rules decide if we've done it correctly. I also need to choose loops, and if you look, it looks like we have three possible loops. We have the left loop, the right loop, and then the entire outside loop. And so I'm just going to label this A, B, and C like we did last time. Only I'm going to do counterclockwise loops this time just to switch it up. So this will be A, this will be B, and this will be C. And let's go ahead and start B right here at junction 2, and we'll start A right here in this corner, and we'll start C down in this corner. So we've chosen random loops and random current directions, and so now we can actually apply the loop and junction rules. So let's go ahead and start with the simpler of the two. Junction 1, we know that the current in must equal the current out, and we can see that from our picture we've got I1 and I2 going into junction 1 and I3 coming out. And so I'll go ahead and write I1 plus I2 equals I3. And that's maybe not so helpful quite yet, but it may help us in the future. We can also go ahead and apply the loop rules. So let's just do it all three just for funsies, where we've got loop A, where we said we're going to start loop A right at this corner here. And remember, we're just going to go, we chose to go counterclockwise this time. So I'm going to go counterclockwise around loop A. And anytime I run into a power supply or a resistor, I know that the total voltage drop of all of those added together must be 0. So we're going to go ahead and apply loop rules to loop A, the loop rule to loop A, where we know that the sum of the voltages around loop A must be 0. And so we could go ahead and say 0 equals, and we're starting again up here and going counterclockwise. So we're going to go down first, and it looks like we'll be going from the high, the positive terminal, to the low, the negative terminal. And the convention for going through a battery is when we go from high to low, we leave with negative voltage or potential difference. So we have minus V1. And then we're going to continue on loop A, where we're going to go through R3. And it looks like we're going to the right through R3, but the current was drawn to the left, so we're going against the current. That means we have to add R3I1. The voltage drop across R3 is IR always. And then we're going to continue on. We have to go up through R1 to continue on loop A. And it looks like we're going up and the current was drawn going down. So we have to add another voltage drop. It would be R1I3. And I think that's it for loop A. If we get back to junction 1 and turn left, we end up where we started. And so that concludes our voltages for loop A. I'm going to go ahead and do one more step here. I'm just going to put in the numbers. Voltage 1 was 100. R3 was 30. And R1 was 500. And so there's our equation for loop A. I'd also like to get an equation for loop B, where we're going to apply the same rules, where the voltage around the entire loop will sum to 0. And so we're going to look at loop B this time. We're starting here and moving counterclockwise around like so. So it looks like we're going to go through V2, then R2, and then R1, and then we'll be all done. So when we follow through loop B, we go through V2 first from low to high. So we're going to add V2. Then we'll continue on, and we'll be going through R2 in the same direction as I2, which means we need to subtract R2I2. And then we're going to continue on and go through R1 in the same direction as I3. And so we'll have to subtract R1I3. And those are the three potential differences or voltage drops that we need to sum to 0. And I'm going to do the same thing where I input the values. R2 was 20. And R1 was 500. And so you can see this time our equations have multiple unknowns, and so it's not quite as straightforward as the last example we did, but that's okay. At this point, we have really enough information to solve the problem. If you remember, one of our rules was, or one of our conventions is that we need, on average, one more loop rule than junction rule to solve the problem. And so this is enough to solve the problem, but because we're doing an example, I'm going to go ahead and get loop C as well, just for practice. So we know the sum of the voltages about loop C is 0. And loop C, we said we're going to start here and just go on the outer loop. So it looks like we're going to have 4 voltages to sum. We go through V2, R2, V1, and R3. And so this one actually will have more variables than the other equations, which makes me a little leery on working through it, but again, we're just practicing. So we're starting here, going counterclockwise around the outer loop. If we do that, we end up getting to V2 first. We're going from low to high, so we're going to add V2. Then we're going to go through R2 in the same direction as I2, so we're going to subtract, just like before. And then we're going to continue on. We're skipping the middle one because we're doing the outer loop. We're forced through V1, going from high to low. So that means we have to subtract. And then from our last resistor, we're going to be going against I1 through R3, so we have to add. So we have to add R3 I1, and there are the 4 voltages that have to sum to 0. So I can go ahead and input those values as well, where we get 3 minus 20I2 minus 100 plus 30I1. And we can combine the 100 and the 3 to get negative 97. And so we have, at this point, completed all of the physics for this problem. We've applied Kirchhoff's rules and gotten all of the equations that we possibly can. We really only needed 2 of these 3, but I just did all of it. And so at this point, I like to say the physics is done. This is worth most of the credit. The rest of this is really just an algebra problem. So there are multiple ways to do this. I'm just going to go ahead and solve it in the way that I like to do it. You're welcome to use calculators to help you, or whatever you choose. I'm going to go ahead and start with our equation for loop A. So loop A, we have this equation here. So I'm just going to rewrite it. So now it's just a math problem. So we're going to start with loop A and see where it takes us. So 0 equals 100, and we have, it's negative 100 plus 30 plus 500. And it's 30I1 and 500I3. So for this, I would probably divide a 10 by everything, and so we'll be also moving this 100 over. So we'll have 10 equals 3I1 plus 50I3 And so I think what I'm going to do, because I'm just like math, I'm going to solve this equation for I1. So I'm going to subtract the 50I3. So we'll have 10 minus 50I3 and divide the whole thing by 3 to get I1. And I'm just going to hold off on that. And now I'm going to look at loop B. Loop B is 3 equals 20I2 plus 500I3. And so for this one, I think I'm just going to go ahead and solve for I2. So we have 3 minus 500I3 over 20 equals I2. And so I just have a couple equations here. And then my junction rule was written as I1 plus I2 equals I3. I1 plus I2 equals I3. And so I've actually gone ahead and written I1 and I2 in terms of I3, and so I'm going to just substitute these in now. So it's, like I said, it just becomes a serious algebra problem more than anything else. So I1 is 1/3 times 10 minus 50I3, right? That is I1. We're going to add I2, which is 1/20 times 3 minus 500I3 equals, and this whole thing equals I3. And so now it's just a little mathemagic. I think what I would do is multiply everything by 60 just to get rid of these ugly fractions. If we multiply everything by 60, we would have 20 times this. So we would have 200 minus 4,000. Oh, I'm sorry. 1,000. 20 times 50 is 1,000, my bad. 3 plus, and then we would have 3 times that would be 9. And minus 1,500 I3 equals 60 I3. And I think if you work through all of this, you'll end up showing that I3 is equal to 209 over 2560 amp. And if we know I3, then we can get any of the others. We can substitute I3 into those other two equations to show that I1. So we could substitute I3 in to show I1 is 1.97 amp. And we could show that I2, and we can use really any rule at this point to get I2, but I2 is negative 1.89 amp. And so I'm going to go ahead and box these in. You might note to yourself, we substituted I3 into here to get I1 and into here to get I2. Or we could have substituted it into here once we had either of the other two. So there's lots of ways to do this. I like to create an answer table to really give our solutions. And we have some more discussion to do on this as well. So we know R1 was the 500, 20, and 30. So we have 500 ohms, 20 ohms, and 30 ohms. We know that I3 goes through R1, I1 goes through R3, and I2 goes through R2. So I'm going to note that I3 goes through R1, I1 goes through R3, and I2 goes through R2. We could note that's from our picture. And so I3 goes through R1. That means I3 is 209 over 2560 amp. This is negative 1.89 amp. And this is 1.97 amp. And I would like to make a note here. This is important. This, the negative, implies that our original I2 direction in our picture is incorrect. This does not mean we go back and change the picture. We need to redraw the circuit with the correct current. This is important. If we go back and redraw the current in this picture, if we just say, oh no, I'm just going to go ahead and change the direction here. This tells me I2 goes this way. Now, if I'm grading you and I look at your picture is wrong relative to all this math that we just did. So we do not want to go through and undo the way that we originally chose our current direction. We need to instead redraw the circuit with the correct directions in the end. But let's go ahead and finish solving this. Well, I can just leave that for you. You should be able to get all of these solutions now just by multiplying. Keep in mind, this should be positive. We're going to ignore the negative when we multiply because we're going to fix the negative in our new picture. So it might be worth noting that the negative implies our original I2 direction is incorrect. And then when we give our final answer, we can redraw it. So in our final answers, we should have this table filled out. Fill it out. And now what we're going to do is redraw our circuit diagram. Where we have our resistors and our power supplies in the same places, but I'm going to choose the correct directions for our currents now. We have I1, I3, and I2, which we have decided is going this way because of the negative sign. So now we've shown the correct direction that the current is going in our circuit. I1 and I3 are going the same way as our original picture because our original picture had positive signs when we calculated the current, so we knew we drew them in the correct direction. Lastly, the problem asks for a real-world application for this. Well, notice that in this circuit, we're forcing current to go the wrong way through the battery. In other words, we're forcing the current from high to low instead of the battery supplying current to the circuit. So oftentimes you use circuits like this to help get energy back into devices that have died. If you force current through the correct type of battery, the battery will store that energy, or in other words, the battery will become charged again. So this is a battery charger. It's not, if anything, it'd be considered a rudimentary battery charger. It's not probably as simple in the real world, but this is the idea. Whenever we force current the wrong way through a battery or the opposite way through the battery, if the battery is designed correctly, it should be able to store that energy, and in other words, we'll be charging the battery. All right, bye.